Right now, 4 human beings are falling back to Earth at 25,000 miles per hour. They just traveled 252,000 miles through the void of space. They came within 467 miles of the lunar surface, close enough to see the craters with their own eyes, close enough to watch the moon fill their windows from edge to edge, close enough that the ancient gray world below them was no longer a disk in the sky, but a landscape, a place, a destination, and they never touched it, not because something went wrong, not because of an emergency, not because of an abort, not because the mission failed, because that was never the plan. Here is what nobody is telling you about Artemis II. Humanity just completed its farthest journey from Earth in over half a century. We broke a record that stood for 54 years, a record, by the way, that was set by a mission that nearly killed everyone aboard. We flew a rocket more powerful than anything built since the Apollo era. We spent decades and tens of billions of dollars developing the spacecraft, the rocket, the ground systems, the trajectory, the procedures. We trained 4 astronauts for years in preparation for this moment, and we came home without a single footprint on the moon. That fact should stop you cold. Because the last time humans were this close to the lunar surface, they were climbing down a ladder. They were picking up rocks. They were leaving behind equipment that is still sitting there today, silent in the airless dark, exactly where it was placed more than 50 years ago. That was 1972. Something happened in the 54 years between then and now. Something that goes far deeper than budgets and politics and engineering timelines. Something that reveals a truth about human capability that is far more unsettling than simple failure. We did not lose the ability to reach the moon. We lost the will to land. If you want to understand what Artemis II actually means, not what NASA is saying in the press releases, not what the headlines are shouting about records broken and milestones achieved, but what this mission quietly reveals about the gap between where we are and where we thought we would be by now, then stay with me tonight, because by the time we are done, the 4,067 miles between the Orion spacecraft and the lunar surface is going to feel like the most significant distance in human history. Not the 252,000 miles that humans crossed to get there. Not the 93 million miles between Earth and the Sun. Not the light years between stars. 4,067 miles, the distance we did not travel. The ground we did not touch. Before we begin, if this kind of deep, unhurried exploration of space and human ambition is what you come here for, take a moment to subscribe. It genuinely helps more than you know. Now get comfortable. Let's begin. Derbrand. Chapter 2. The Power Behind Artemis II, the Temister. On April 1st, 2026, at exactly 6:35 in the evening Eastern Time, the Space Launch System rocket ignited its engines at Launch Complex 39B at Kennedy Space Center in Florida. The numbers alone are staggering, but I want you to feel them rather than just process them. The SLS generates 8.8 million pounds of thrust at liftoff. To put that in terms your body can understand rather than just your mind, that is roughly equivalent to the combined force produced by approximately 160,000 car engines firing simultaneously. If you took every car currently sitting on every highway in the state of Florida and somehow ignited all of their engines at the same instant and pointed them in the same direction, you would approximate the force that lifted the Artemis II mission off its launch pad. The twin solid rocket boosters, the 2 long white cylinders bolted to either side of the massive orange core stage, are themselves an engineering achievement that deserves separate attention. Each one burns through approximately 5 tons of propellant per second. Each one generates more thrust individually than the entire Saturn rocket that carried Apollo astronauts to the moon in 1969. The Saturn V which remains in many ways the greatest rocket ever built, which lifted 130 tons to low Earth orbit and sent humans beyond it, which produced 6 million pounds of thrust. Each of the SLS's solid rocket boosters exceeds that number on its own. The entire vehicle, fully fueled and loaded for flight, weighs 5.75 million pounds. That is heavier than 4 fully loaded Boeing 747 jumbo jets stacked on top of each other. It is one of the heaviest objects humanity has ever deliberately thrown into the sky. Standing next to the vehicle on the launch pad, you could not see its top without craning your neck back at an angle that would make you dizzy. The rocket stands 322 feet tall, taller than the Statue of Liberty from base to torch, taller than a 30-story building, taller than anything else currently being launched into space anywhere on Earth. And it worked. The launch was, by the accounts of everyone who watched it and everyone who flew it, almost shockingly smooth. Pilot Victor Glover, speaking from space the following day during a live public affairs event, said the crew had trained themselves not to have expectations, but admitted that in the back of his mind, he had quietly hoped they would actually launch, because that is the reality of spaceflight. Even after decades of preparation, even after thousands of hours of simulation, even after years of delayed launch attempts and frustrated timelines, you never quite believe it is real until the engines light and the ground falls away beneath you. The SLS had earned a reputation as a rocket that was difficult to get off the ground. Its first 2 launch attempts for Artemis in September 2022 were scrubbed due to technical issues, an engine bleed problem, and then a hydrogen leak. Weather delays pushed the uncrewed mission further. For Artemis II, with actual human crew aboard, the pressure to get it right was exponentially higher. Launch controllers were prepared for scrubs. The mission management team had contingency plans for contingency plans. Instead, the countdown proceeded cleanly. The first terminal sequence executed precisely. At T0, the 4 RS-25 engines at the base of the core stage, the same fundamental engine design that powered the Space Shuttle program for 30 years. Engines so well understood that their performance characteristics had been characterized across hundreds of firings, ignited first, followed immediately by the solid rocket boosters, and 8 million pounds of thrust pushed the vehicle off the pad. Within about 90 seconds, the vehicle had exceeded the speed of sound. Within 2 minutes, the solid rocket boosters had expended their propellant and separated, tumbling away into the Atlantic as the core stage engines continued to burn. Within 8 minutes of liftoff, the core stage had burned through its own propellant and separated from the vehicle. The 4 RS-25 engines cut off, the stage fell back toward the Atlantic Ocean, and the Orion spacecraft, named Integrity by its crew, was now coasting in a parking orbit around Earth, approximately 100 miles above the surface, preparing for the burn that would send it toward the moon. That burn, called the translunar injection, came roughly an hour and a half after launch. The interim cryogenic propulsion stage, a liquid hydrogen and liquid oxygen upper stage sitting between the core stage separation point and the Orion spacecraft, fired its engine for 5 minutes and 49 seconds. That burn accelerated the spacecraft from orbital velocity to approximately 24,500 miles per hour, enough to break free of Earth's gravitational well and begin the long curving arc toward the moon. From that moment, the 4 astronauts aboard, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency mission specialist Jeremy Hansen, were committed to the trajectory. There was no turning back without a significant engine burn. The moon was pulling them forward, Earth was falling behind, and the 252,000-mile journey had truly begun. The crew had approximately 4 hours of sleep before launch. They had spent the preceding days in the crew quarters at the Neil Armstrong Operations and Checkout Building, running through final medical checks, reviewing procedures, sitting through weather briefings, waiting for the moment when everything would finally be real rather than simulated. When the engines lit, Commander Wiseman later said, "It felt less like relief and more like inevitability, as though the years of preparation had been building toward a single instant of ignition, and now that instant had arrived, the only possible thing to do was fly." Here is the thing about that number, 252,000 miles. It sounds enormous, and in human terms, in the terms of roads and oceans, and the distances between cities and the durations of airplane flights and the range of car trips, it is enormous. Light at 186,000 miles per second would cross that distance in slightly over 1 second. A commercial airplane flying at 575 miles per hour would need approximately 18 months of continuous flying to cover it. A car on an interstate highway, never stopping for gas or sleep or food, would need nearly 40 years. By the standards of everyday human experience, 250,000 miles is essentially unimaginable. And by the standards of the universe, it is nothing at all. The moon sits on average 238,855 miles from Earth. The distance varies because the moon's orbit is not perfectly circular. It is slightly elliptical, an oval shape that brings the moon closer at some times called perigee and farther at others called apogee. The difference between closest and farthest is about 30,000 miles. Artemis II flew a trajectory that took the crew slightly beyond the moon, looping around in a free return arc that required no additional engine burns to ensure the spacecraft would return to Earth even in the case of propulsion failure, a trajectory choice made explicitly to maximize crew safety. The maximum distance from Earth reached by the Artemis II mission was 252,021 miles. That number broke a record that had stood since 1970. A record that was set not in triumph but in desperation. To understand why, we need to go back, not to Apollo 11, the triumph, not to Armstrong and Aldrin and their boot prints and their flag, and the impossible grainy television images that billions of people watched in real time. We need to go back to a darker moment, a moment when the moon nearly became not a destination but a tomb. Dubbergrind, Chapter 3. The wrecker that was never meant to exist. Dubbergrind, April 11th, 1970. Kennedy Space Center, Florida. Apollo lifts off on a Saturn V rocket, carrying astronauts Jim Lovell, Jack Swigert, and Fred Hayes toward the moon. Lovell is on his 4th spaceflight. He flew on Gemini 7, Gemini 12, and Apollo 8, the first mission to carry humans to lunar orbit. He is one of the most experienced astronauts alive. Swigert joined the mission late, replacing Ken Mattingly after a flight surgeon determined that Mattingly had been exposed to German measles and was at risk of developing the illness during the flight. Hayes is on his first spaceflight. The mission plan calls for a landing in the Fra Mauro Highlands, a geologically ancient and scientifically important region of the lunar surface. Scientists believe the Fra Mauro Formation contains material ejected from the Imbrium Basin impact, one of the largest impact events in the moon's history, and that studying its rocks would provide a window into the earliest history of the solar system. This is the science that justified the risk, the investment, the years of development. The launch is nearly perfect. The first stage burns correctly. The second and third stages perform as planned. The translunar injection burn sends the spacecraft on its arc toward the moon. By April 13th, the crew is approximately 200,000 miles from Earth and closing on the moon, executing the routine procedures of a mission that everyone expects to go as smoothly as Apollo 12 before it. Then at 9:08 in the evening Houston time, Mission Control instructs Jack Swigert to perform a routine stir of the oxygen tanks in the service module. It is a standard procedure, a piece of routine housekeeping done to prevent the liquid oxygen from stratifying. It takes seconds. It has been done dozens of times on previous missions without incident. This time, insulation on the wiring inside oxygen tank number 2. Insulation that was damaged during ground testing months earlier, damage that was never detected, allows a spark to ignite inside the tank. The tank explodes. The force of the explosion ruptures oxygen tank number 1 as well. The service module is breached. The fuel cells that generate electricity and water for the spacecraft, which require oxygen to operate, begin to fail. Within minutes, the command module Odyssey is losing power at a rate that cannot be stopped. The crew has hours, not days, before it goes completely dark. Swigert's transmission to Mission Control has become one of the most famous understatements in the history of exploration. "Houston, we've had a problem." The moon landing is instantly abandoned, not with regret, not with deliberation, not with meetings and risk assessments and management reviews. It is abandoned in the time it takes Mission Director Gene Kranz to understand what he is being told. Survival is now the only objective. The question has shifted from how do we get these men to the surface to how do we get these men home. Mission controllers in Houston face a problem without precedent. The spacecraft has already traveled too far from Earth to simply turn around and come back directly. The fuel required for a direct return does not exist. The trajectory back to Earth via direct abort would require more propellant than the damaged spacecraft can provide. And time is critical. Every hour that passes is an hour in which the crew's situation can only deteriorate. The fastest way home, the only realistic way home given the constraints of fuel and trajectory and time, is to continue toward the moon, use the moon's gravity to sling the spacecraft around the far side and redirect its momentum back toward Earth and ride the return arc home. This maneuver is called a free return trajectory. The spacecraft will swing around the moon, and the moon's gravity will bend its path back toward Earth without requiring a major engine burn. It works. 3 desperate days of improvised problem-solving follow. Rationing power, reducing CO2 in the atmosphere, navigating by starlight. But the physics works. Jim Lovell, Jack Swigert, and Fred Hayes survive. They splashed down in the South Pacific on April 17, 1970, cold and dehydrated and exhausted but alive, in one of the most extraordinary survivals in the history of human exploration. But the physics of that rescue created a side effect that nobody planned for and nobody celebrated. The trajectory required to save Apollo 13 swung the spacecraft around the far side of the moon at its maximum distance from Earth. During that swing, the crew reached 248,655 miles from Earth. This was farther from Earth than any human being had ever traveled. Farther than any astronaut on Apollo 8, which had been the first crewed mission to lunar orbit. Farther than the crew of Apollo 11, who had actually landed. Farther than anyone before or since. The crew of Apollo 13 set the record for the farthest distance from Earth in human history, not through daring or exceptional ambition or extraordinary planning. They set it because their oxygen tank had exploded and they were trying not to die. The record was a byproduct of desperation. It was the distance forced upon them by a rescue maneuver, not chosen by them in pursuit of exploration. That record stood for 56 years. Think about what 56 years contains. The first personal computers were built, sold, and replaced by systems a billion times more powerful. The internet was invented, expanded, and became the primary medium of human communication. Humans decoded the human genome. Robotic spacecraft visited every planet in the solar system, landed on Mars multiple times, flew past Pluto, crossed the edge of the solar system itself. The Hubble Space Telescope was launched, repaired by spacewalking astronauts, and spent decades photographing the universe back to within the first billion years after the Big Bang. The James Webb Space Telescope was launched, reaching its operating point 1 million miles from Earth, and began returning images of galaxies older than anything previously observed. In those same 56 years, no human being got as far from Earth as 3 men on a broken spacecraft who were simply trying to get home. On April 6, 2026, the Artemis II crew reached 248, 656 miles from Earth, 1 mile beyond Apollo 13's record. They continued outward to their maximum distance of 252,021 miles. They broke the record deliberately, intentionally, with a healthy spacecraft and a crew that knew exactly where they were going and how they were getting home. The press releases called it historic, and it was. But here is what the press releases did not say. Apollo 13 set its record while trying desperately to reach the lunar surface. Jim Lovell and Fred Hayes had trained for months to walk on the moon. They had studied the Fra Mauro geology. They had practiced the surface operations. They had prepared for the landing with the same intensity that every Apollo crew prepared, because landing on the moon is what they were going there to do. The oxygen tank explosion took that away from them. Every mile of the agonizing return journey was a mile they traveled because their mission had been destroyed by mechanical failure. Artemis II set the new record while never planning to land at all. The farthest humanity has ever traveled from Earth. On both occasions, we were not standing on another world. We were flying past it or limping home from a disaster. We have broken every distance record in the history of human spaceflight without once, in the act of breaking the record, planting both feet on the surface we were supposedly trying to reach. This is not an indictment, it is a fact, but it is a fact worth sitting with for a moment before we move on, because it contains something important about the relationship between proximity and arrival, between being close and actually being there, that runs through the entire history of human lunar ambition. Dubrindrend. Chapter 4, 4060 sea vials. Severnbrindren. Let us talk about the distance that matters most in this story. Not 252,000 miles, not 238,855 miles, not the 93 million miles between Earth and the Sun, not the nearly 4 trillion miles to the nearest star, 4,067 miles. That is how close the Artemis II crew came to the lunar surface at their closest approach. On April 6, 2026, as the Orion spacecraft swung around the near side of the moon in preparation for the powered flyby that would set its trajectory for the return to Earth, the 4 astronauts looked out of their windows at a world they had traveled 250,000 miles to see. And what they saw was not the moon of postcards and textbooks. That small, bright circle hanging in a dark sky, so familiar that it hardly registers as a world at all. What they saw was a landscape, a place with geography and texture and age. Christina Koch, who had spent 328 days aboard the International Space Station and who had performed multiple spacewalks in low Earth orbit, described looking out those windows as being transported somewhere beyond language. She had seen Earth from orbit many times. She had watched the Terminator, the line between day and night, sweep across continents. She had seen thunderstorms from above, had watched the aurora borealis from outside the atmosphere, had looked down at the Himalayas and the Sahara and the Pacific Ocean with the intimacy that only orbital altitude provides. She thought she understood what it meant to look at a world from space. The moon, at 4,067 miles, was something different. The moon filled the glass from edge to edge, not a disk against the blackness, but a surface, vast, textured, terrifyingly detailed, occupying the entire field of view and then some. She could see individual features with her naked eye. She could pick out the shadows pooling in the floors of craters, the sharp rims of recent impacts against the worn softness of older terrain, the wrinkled ridges of ancient lava flows that solidified billions of years ago and have not moved since. She could see the texture of the regolith, the fine-grained layer of impact-pulverized rock that covers the entire surface, in the way that low-angle lighting creates shadows on a sandy beach, giving depth to what would otherwise appear flat. Victor Glover said, "The experience reaffirmed his most deeply held beliefs about the fragility of Earth and the responsibility that comes with being able to see it." He described a moment during the lunar flyby when he turned from the moon to look back at Earth, now reduced to a blue disk smaller than his thumbnail held at arm's length. He had seen Earth from the space station. He had watched it roll past the windows during 6 months in orbit, but from 252,000 miles, it was something else. It was small in a way that was not just visual but philosophical. It was small in the way that forces a reckoning. Commander Reed Wiseman said something more spare and perhaps more revealing. He said that when the lunar flyby began and the moon filled the windows, the crew fell silent for a moment, not from awe, though there was awe, from something harder to name. He called it the silence of understanding. The crew knew they were not going to land. They had known this since the beginning. It was not a surprise, not a disappointment in the mission-failed sense. But seeing the surface that close, being that close to it, made the fact of not landing into something more concrete than it had been during training. During training, not landing was a technical specification. At 4,067 miles, not landing was an experience. 4,067 miles. Here is what that distance means in terms you can put your body inside. 4,000 miles is roughly the distance from New York City to London, measured great circle across the North Atlantic. It is approximately the width of the continental United States plus another 500 miles of Pacific Ocean beyond the California coast. It is the distance from Moscow to Tehran, from Beijing to Sydney, from Cairo to Johannesburg. It is a long flight. It is a journey that a commercial airliner covers in about 7 hours, burning approximately 120,000 pounds of jet fuel, carrying 200 or 300 people who mostly spend the time watching movies and eating airline food, and barely registering the extraordinary fact that they are hurtling through the stratosphere at 500 miles per hour. People cross 4,000 miles every day, millions of times per day, without thinking about it, without considering it remarkable, without feeling the distance as anything other than a temporary inconvenience. In space terms, 4,067 miles is almost nothing. The International Space Station orbits Earth at an altitude of roughly 250 miles. The Artemis II closest approach to the Moon was more than 16 times farther from the lunar surface than the ISS is from Earth's surface. By the standards of interplanetary distances, by the standards of the solar system, by the standards of anything beyond our homeworld, 4,067 miles is a rounding error. And yet, here is what those 4,067 miles actually represent in human terms. That gap, that specific measured, deliberate gap between the Orion spacecraft and the surface of another world, is the entire distance between visiting and arriving, between observing and touching, between proximity and presence, between being a witness to another world and being part of it. The Apollo astronauts who landed on the Moon reduced that gap to zero. Not 4,067 miles, not 4 miles, not 4 feet, zero. They closed it completely through a sequence of maneuvers that required leaving one spacecraft in orbit, descending in another to the surface, touching down at velocities low enough not to destroy the landing gear, and stepping out onto the ground. 12 human beings did this between July 1969 and December 1972. 12 people closed the gap entirely. They picked up rocks. They set up scientific instruments. They drove a rover. They left behind retroreflectors that scientists still bounce lasers off today to measure the moon's distance from Earth with millimeter precision. Then the gap opened again. Slowly, silently, without ceremony, it opened. The Apollo program ended. The lunar module production line shut down. The engineers who knew how to land on the moon retired or moved to other programs. The institutional knowledge dispersed, and the gap between any human being and the lunar surface grew back to its natural size, the full 238,855 miles, and stayed there for 54 years, brought it down to 4s and 60s, close, historically close, closer than any human has been in over half a century, close enough to see individual surface features, close enough that the lunar gravitational field measurably affected the spacecraft's trajectory and had to be precisely accounted for in the navigation calculations. Close enough that Christina Koch and Reed Wiseman and Victor Glover and Jeremy Hansen could look out their windows and see a world, not a light in the sky, not a disk in the darkness, but a world with terrain and history, but not to zero. The question that should haunt anyone thinking seriously about this mission, about what it represents in the arc of human history and human ambition, is not how humanity closed the gap to 4,067 miles. We know how the SLS worked, the Orion worked, the trajectory was planned and executed. The answer to that question is engineering, and it is known. The question is why, after everything, after the SLS and the Orion and the billions of dollars and the years of delay and the generations of engineers who dedicated their careers to this program, the plan was never to close the gap all the way on this mission. And the answer to that question is both more technical and more human than most people realize. Dutbrenbrenland. Chapter 5. Why Orion Cannot Land. Distabrenunabrenland. The Orion spacecraft was not designed to land on the moon. That statement, stated plainly, might seem like a simple engineering observation. Of course, a spacecraft optimized for one purpose is not optimized for another. Of course, you would not use a passenger jet to plow a field. But the implications of that design choice run deeper than a simple trade-off. And understanding them requires understanding what landing on the moon actually demands of a spacecraft, and why those demands are so difficult to meet. To land on the moon, you need to do something that sounds straightforward. Slow down. The moon has no atmosphere. This single fact shapes everything about lunar landing and makes it fundamentally different from landing anywhere on Earth. On Earth, returning spacecraft rely primarily on aerodynamic drag to shed the enormous kinetic energy they carry from orbital or interplanetary velocities. The atmosphere does most of the work. Heat shields glow and ablate. They sacrifice layers of material to carry away heat, and by the time a capsule has decelerated from 25,000 miles per hour to a speed where parachutes can deploy, it has lost most of its dangerous velocity through interaction with the air, without burning a single gram of rocket propellant. The moon offers none of this. There is no air. There are no air molecules to push against, no aerodynamic drag to exploit, no way to use atmospheric braking of any kind. Every foot per second of velocity that a lunar landing spacecraft needs to lose must be lost through rocket thrust, through burning propellant and directing the exhaust in the opposite direction of travel. Pure, direct, propellant-intensive thrust. A spacecraft arriving at the moon from lunar orbit is moving at roughly 3,700 miles per hour relative to the lunar surface. Every bit of that speed must be countered by engines firing in the opposite direction, continuously, all the way from orbit to touchdown. This requires an enormous amount of propellant. That propellant requires tanks to hold it. The tanks require structure to contain them. All of that structure and propellant adds mass, and more mass requires more propellant to slow it down, which requires more tanks, which adds more mass, which requires more propellant. This recursive loop is called the tyranny of the rocket equation, and it is the fundamental physical constraint that makes landing on the moon so much more difficult and expensive than simply flying to it. The Apollo lunar module was a masterpiece of engineering specifically designed to break this loop at the minimum possible mass. It was divided into 2 stages for exactly this reason. The descent stage, the lower half of the vehicle, the spidery-looking arrangement of legs and fuel tanks and a central engine, carried a descent propulsion engine and enough propellant to slow from orbital velocity down to a gentle touchdown, consuming itself in the process. It provided the landing legs that absorbed the final impact with the surface and allowed the vehicle to stand stably on the regolith. It carried the scientific equipment, the power systems, the tools the astronauts needed for surface operations, and it was designed to be abandoned. Once the crew was ready to leave, the descent stage became a launch platform and nothing more. The ascent stage, the top half, the roughly rectangular box where the crew lived during the surface stay and the journey back to orbit, was stripped to the absolute minimum possible mass. The astronauts stood during ascent because seats were too heavy to justify. The walls were made of materials so thin, in some places, aluminum as thin as 2 sheets of household aluminum foil, that crew members were warned never to lean against them too forcefully for fear of puncturing the hull. The windows were small. The systems were minimal. The ascent stage carried only what was absolutely necessary to lift 2 people from the lunar surface, reach orbital velocity, and dock with the command module waiting above. The total fueled mass of the Apollo lunar module was approximately 33,500 pounds. It was a purpose-built machine with a single objective: get 2 people to the surface, get them back to orbit, and dock. It could do nothing else. It had no heat shield because it never needed to re-enter an atmosphere. It had landing legs because it needed to stand on an uneven surface covered with loose, fine-grained regolith whose load-bearing properties were uncertain before the first landing. Every gram, every design decision, every trade-off was subordinated to the single goal of landing, and ascending from the moon at the minimum mass Orion is something categorically different. Orion is designed to carry crew through deep space and return them safely to Earth across the full range of trajectories that the Artemis program will require, from lunar flyby to lunar orbit to eventual Mars trajectories. It has a heat shield, not just any heat shield, but one of the largest ablative heat shields ever built, capable of handling re-entry speeds significantly higher than those experienced by returning shuttle missions, because lunar return trajectories involve higher speeds than low Earth orbit missions. It has a service module provided by the European Space Agency that wraps around the capsule and carries the main propulsion system, power generation, thermal control, and life support consumables for the journey. It has 4 seats. It has room for 4 crew members and their equipment and their food and their personal items and the scientific instruments required for the mission. It is built to the standards of a vehicle that humans will depend on to keep them alive for up to 21 days. What it does not have is landing legs. It does not have a descent propulsion system capable of slowing from orbital velocity to 0 thrust above the lunar surface. It does not have the structural systems required to survive the mechanical stresses of a lunar touchdown. It was not designed for any of those things, and it could not be redesigned to include them without fundamentally changing what it is, because the mass required to add landing capability would exceed what the SLS can deliver to lunar orbit. The Artemis program architecture places the landing function on a completely separate vehicle, the Human Landing System, that launches independently, meets Orion in lunar orbit, receives the crew through a docking interface, descends to the surface with the crew aboard, ascends back to orbital altitude with the crew, redocks with Orion, and transfers the crew back for the journey home. This two-vehicle architecture is conceptually similar to the Apollo architecture, where the Command Seas module and the lunar module were always separate vehicles that met in orbit. The human landing system for Artemis has been contracted to SpaceX, which is developing a lunar-optimized variant of its Starship vehicle for this purpose. Starship is an extraordinary machine in its own right, the largest and most powerful rocket system ever built, capable of carrying enormous payloads to orbit, but adapting it for lunar landing involves challenges that have taken longer to solve than the program's original schedule anticipated. And this is the reason Artemis II did not land. The human landing system was not there, not because it does not exist. It exists, it has been developed, elements of it have been tested, but it has not yet demonstrated the complete capability required to carry crew from lunar orbit to the surface and back, to dock with Orion in lunar orbit, to perform the full sequence of operations required for a crewed landing mission. Those demonstrations are planned for Artemis III. Until they happen, until the complete system has been verified and qualified, the gap between Orion in lunar orbit and the lunar surface, those 4,067 miles, cannot be safely closed. Here is what this means in simple terms. The Artemis II crew had everything they needed to reach the moon's vicinity. They had the rocket to get there and the spacecraft to sustain them. What they did not have was the taxi from the spacecraft to the surface. And without the taxi, 4,067 miles is not a small gap. It is an uncrossable one. The gap is not about distance, it is about infrastructure, and the infrastructure is still being built. Drone. Chapter 6. The Heat Shield nobody talked about, Stumdrune. Before we continue into the deeper history of why humans left the moon and struggled to return, there is something about Artemis II itself that received almost no serious coverage in the mainstream press. Something that adds a layer of tension to the mission that goes beyond the engineering rationale for not landing. Something that connects this mission, uncomfortably but undeniably, to some of the darkest moments in the history of human spaceflight. The Orion spacecraft's heat shield had a problem that engineers had not fully resolved before the mission flew. Let me take you back to December 2022. Artemis I, the uncrewed test flight that preceded Artemis II, completed its mission, and the Orion capsule re-entered Earth's atmosphere for the first time under real mission conditions. The re-entry was successful. The capsule was recovered from the Pacific Ocean. The mission was declared a success. But when engineers examined the heat shield carefully after recovery, they found something they had not expected and could not immediately explain. The ablative material that makes up the heat shield, a substance called AVCO, a mixture of silica fibers and epoxy resin that is packed into a honeycomb structure bonded to the capsule's base, had eroded in a pattern that did not match the predictions of the thermal models. Chunks of material had broken away, not small amounts of material, but chunks, pieces of the heat shield that had separated from the structure and been lost during re-entry. The models had predicted gradual, relatively uniform erosion as the material charred and ablated in the expected manner. What engineers found was irregular, non-uniform erosion with localized regions of significant material loss. The heat shield had worked. The capsule was recovered intact, and the crew, had there been one, would have survived. But the difference between what was predicted and what actually happened was large enough that engineers could not simply note the discrepancy and move on. If you do not understand why your heat shield behaved differently than your models predicted, you do not know whether the models are wrong in ways that matter for future flights. and you cannot be confident that future re-entries will be safe. The investigation that followed took months. Engineers examined physical evidence from the recovered heat shield. They ran computational fluid dynamics simulations. They consulted materials scientists and aerothermodynamics experts, and they identified a leading hypothesis for the anomalous erosion: moisture. During ground processing, during the months that the heat shield spent in the vehicle assembly building and on the launch pad before the mission, moisture had apparently penetrated into the AV coat material. The material is designed to be dry, but the honeycomb structure that holds the AVOT provides pathways through which atmospheric moisture can migrate under certain conditions. When the heat shield was exposed to the extreme temperatures of re-entry, this moisture vaporized rapidly. The sudden expansion of water vapor within the material may have contributed to the irregular, localized failures that produced the unexpected erosion pattern. The solution engineers proposed was a modification to the manufacturing process for future heat shields, a change in how the AVCate was processed and sealed to reduce moisture permeability. Test the modified material, characterize its performance, verify the fix with ground testing before flying it. Here is where the decision became genuinely difficult. Implementing the fix for Artemis II's heat shield would have required time, significant time. The modified manufacturing process needed to be developed, validated, applied to the actual flight hardware, and the hardware then needed to be inspected and certified. Given the delays that had already accumulated in preparing the Artemis II mission, delays caused by heat shield issues, by SLS processing challenges, by schedule pressure from the agency, by the simple complexity of preparing the most capable crewed spacecraft in American history for its first human flight, implementing the fix would have pushed the launch date back further. Perhaps significantly further, NASA faced the choice that aerospace programs always eventually face when schedule pressure meets technical uncertainty: delay to achieve higher confidence, or proceed with known uncertainties. While accepting that the risk cannot be fully characterized, NASA chose to fly. The decision was made after an extensive review process. Engineers presented their analysis. Safety panels deliberated. Outside experts were consulted. NASA leadership studied the data and the arguments. The conclusion was that the existing heat shield design, with the known anomaly from Artemis provided sufficient margin for a safe re-entry on Artemis II, even accounting for the uncertain physics of the APT erosion. The plan to implement the fix for Artemis III was formalized. The mission was cleared to proceed. Some of the engineers who had raised concerns were, after reviewing the additional analysis, satisfied that their questions had been addressed. Others were not. Some continued to object to flying the mission without a redesigned and retested heat shield. Their objections were noted. The mission proceeded over those objections. On April 10, 2026, the Orion spacecraft named Integrity completed its re-entry sequence above the Pacific Ocean. The heat shield performed. The capsule survived. The 4 crew members splashed down safely off the coast of San Diego. But I want to stay with the decision for a moment, because the outcome, successful, does not resolve the question the decision raises. When engineers identify an anomaly with a thermal protection system and raise safety concerns, and the program decides to fly over those concerns, and the mission succeeds, the temptation is to conclude that the decision was correct. The heat shield worked. The concerns were excessive. The engineers who wanted to delay were being too cautious. This conclusion is not supported by the logic of the situation. A decision made under uncertainty that happens to produce a good outcome is not necessarily the right decision. We can only evaluate the decision with the information available at the time it was made. And at the time NASA decided to fly Artemis II with the existing heat shield, Engineers with direct knowledge of the system had unresolved concerns about its behavior under re-entry conditions. There is a name for the cognitive error that treats a successful outcome as validation of the decision that led to it. It is called outcome bias, and the history of human spaceflight contains examples of outcome bias leading to catastrophic consequences, precisely because the positive outcomes that accumulate over time create false confidence in decisions that were actually unsafe. February 1st, 2003, the Space Shuttle Columbia is executing re-entry over the Pacific Ocean 16 days into a science mission. The crew has been in orbit since January 16th. During launch, a piece of foam insulation, approximately 67 pounds of foam, broke away from the external tank and struck the leading edge of the left wing at approximately 530 miles per hour. The impact damaged the reinforced carbon-carbon thermal protection tiles that shield the wing from re-entry heating. Engineers noticed the foam strike in the launch camera footage and raised concerns. An analysis team assembled, reviewed the available imagery, and attempted to assess the damage. They concluded, based on limited information and analysis methods that were later found to be inadequate, that the damage was acceptable and that the mission could proceed safely to re-entry. Some engineers disagreed. Some wanted to request additional imagery from military satellites that might have revealed the extent of the damage. Those requests were not pursued with sufficient urgency. The safety concern was managed down rather than resolved. During re-entry, superheated atmospheric gas entered the damaged wing through the breached tile. The wing structure failed. The vehicle broke apart over the southwestern United States at an altitude of about 200,000 feet. At a speed of approximately Mach 18, all 7 crew members, Commander Rick Husband, pilot William McCool, mission specialists Kalpana Chawla, Laurel Clark, and David Brown, payload commander Michael Anderson, and Israeli astronaut Ilan Ramon died. The parallel between Columbia and Artemis II is not perfect. The nature of the thermal protection anomaly was different. The severity of the known damage was different. The analysis methodologies have been improved significantly in the 2 decades since Columbia. The margins were assessed differently, but the structural similarity is real and important. In both cases, an anomaly with a thermal protection system was identified. In both cases, engineers raised concerns. In both cases, a formal review was conducted and a decision was made to proceed. In both cases, the program flew. One of those decisions led to the loss of 7 lives, the other did not. The Artemis II crew is home. The mission was successful, the heat shield performed, and we should carry the knowledge of how close the 2 situations were in structure, how similar the decision process was, and how different the outcomes could have been, not as a condemnation of NASA's decision, which was made in good faith with thorough review, but as a reminder that success in spaceflight is never guaranteed, and that the decisions made at the margins of acceptable risk are the most consequential decisions in the history of exploration. Dubrind Drund. Chapter 7. How We Lost the Moon. Stubrimlandsrent, December 14, 1972. Commander Gene Cernan stands on the surface of the moon for the last time. He is preparing to climb back up the ladder of the Apollo 17 lunar module, to leave behind the Taurus Littrow Valley and the regolith that has coated his suit and tools and the rover wheels in fine gray dust. He has been on the surface for the better part of 3 days with geologist Jack Schmidt. They have collected 243 pounds of lunar samples, the largest sample collection of any Apollo mission. They have set up the most sophisticated suite of surface instruments deployed by any crew. They have driven the rover farther and explored more terrain than any previous landing. Now, Cernan pauses at the base of the ladder. He takes one final photograph of his boot print in the lunar soil. He scrapes his boot across the regolith one last time, as though marking the moment with a physical gesture, pressing human presence into a surface that recorded it perfectly and permanently. The moon has no weather to erase it. The boot print will be there in 1,000,000 years, in 1,000,000,000 years, preserved in the same airless, changeless medium where it was made. He climbs the ladder. The ascent stage lifts off. The surface of the moon falls away beneath him. Gene Cernan is the last human being to have stood on the surface of another world. As of April 2026, he remains the last. The boot print he left behind has outlasted him. He passed away in 2017 and continues to exist in the lunar regolith unchanged. The end of the Apollo program was not the result of a single dramatic decision. It was the product of a slow accumulation of pressures, priorities, and redirections that stretched across the late 1960s and early 1970s, each individually rational but collectively amounting to the abandonment of something extraordinary. To understand how this happened, you need to understand what Apollo actually was and what it was not. Apollo was not primarily a scientific program. It was not built by NASA scientists who convinced Congress that lunar geology was sufficiently important to justify the largest peacetime mobilization of scientific and engineering talent in American history. The science was real and valuable. The samples collected by the 6 landing missions transformed our understanding of the moon's formation and the early solar system, but science alone would not have funded the Saturn V rocket, or the lunar module, or the mission control infrastructure, or the 400 people employed across the contractor base. Apollo was built by a Cold War. President Kennedy's May 1961 speech committing the United States to landing a man on the moon before the end of the decade was delivered less than 2 months after Yuri Gagarin became the first human in space. It was delivered in the context of the Berlin crisis, of Soviet military adventurism, of an American public increasingly anxious about falling behind the Soviet Union in a competition that felt existential. The moon was the arena because it was the most visible, most dramatic stage on which national technological capability could be demonstrated. The United States was going to the moon because the Soviet Union had beaten them into orbit, and they needed to beat the Soviet Union to something. By 1969, the demonstration had been made decisively. Apollo 11 landed on the Sea of Tranquility, and the Soviets had nothing to match it. Their own lunar program, which the Soviet government publicly denied had ever existed, a denial maintained for decades, had failed to deliver a human to the moon and was being quietly wound down. The geopolitical purpose of Apollo had been achieved. What remained was the science, the exploration, and the intrinsic human value of extending our presence to another world. These objectives, it turned out, could not sustain the political will to fund one of the most expensive peacetime endeavors in American history indefinitely. Apollo cost approximately $25 billion in 1960s money. The numbers vary depending on what you include in the calculation, but inflation-adjusted estimates range from roughly $150 billion to over $280 billion in current terms. At its peak, the program consumed nearly 4% of the total federal budget. It employed approximately 400,000 people directly and across the contractor base. Engineers, scientists, technicians, managers, factory workers, test pilots, and the vast support infrastructure required to sustain them. By the early 1970s, the political situation that had generated the will to sustain that investment had changed. The Vietnam War was consuming hundreds of billions of dollars and generating massive public protest. The Great Society social programs were competing for federal resources. Inflation was rising. The economy was under pressure. And the moon, which had seemed like the most urgent frontier in 1961, had already been reached. The urgency was gone. Apollo 18, 19, and 20 were on the schedule and had hardware partly built. They were canceled in September 1970. The decision was made not because the missions were impossible or likely to fail, but because the budget had to be cut somewhere, and missions that had already partially achieved their purpose seemed like a reasonable place to cut. The remaining Apollo missions, 14, 15, 16, and 17, flew because their hardware was already complete, and canceling them would have meant writing off billions of dollars of existing investment. When Apollo 17 lifted off from the moon in December 1972, it was not the triumphant departure of a program at the height of its powers preparing for the next phase. It was the last gasp of a program that was already being wound down, whose successor had not been defined, whose infrastructure was being deliberately deconstructed. The production lines for the Saturn V's F1 engines, the most powerful rocket engines ever built, still unmatched in thrust per engine more than 50 years later, were shut down. The tooling was scrapped. The technical documentation was archived. But the people who understood how to interpret that documentation and who knew the subtle, undocumented knowledge accumulated through years of manufacturing and testing were allowed to retire, to disperse, to take other jobs. The institutional knowledge that had made Apollo possible did not survive in usable form. What followed Apollo was the Space Shuttle program, an extraordinary technological achievement in its own right, but one that by design kept humans in low Earth orbit. The shuttle could not go to the moon. It was not designed to. Its purpose was to make access to low Earth orbit routine and economical, to build the International Space Station, to launch and service scientific satellites. It flew 135 missions over 30 years, conducted thousands of hours of scientific research, deployed and repaired the Hubble Space Telescope, and demonstrated that humans could live and work in space for extended periods. But it never went back to the moon. Then, in January 2004, President George W. Bush announced the vision for space exploration, a plan to retire the shuttle, develop a new spacecraft and heavy lift rocket capable of going to the moon, and eventually send humans to Mars. The new program was called Constellation. Development began. The Ares rockets and Orion capsule took shape. In 2010, President Barack Obama canceled Constellation. The billions spent on development were written off. The program ended. A new direction was announced, focused on commercial spaceflight, asteroid missions, and eventually Mars by the 2030s, without a return to the moon as an explicit intermediate goal. In 2017, the Trump administration established the Artemis program, explicitly targeting a return to the moon by 2024. The Orion capsule, which had survived the cancellation of Constellation, was retained. A new heavy lift rocket was developed, the Space Launch System, using much of the same hardware base as the canceled Ares rockets. Commercial landers were contracted. The 2024 goal was not met. The target slipped to 2025, then 2026, then some uncertain point after 2026. In April 2026, the first crewed Artemis mission flew to the moon's vicinity. It did not land. This is the history behind the 4,067 miles. Not just the engineering decisions made in the design of Orion and the human landing system, but the 54 years of political decisions, program cancellations, institutional knowledge losses, budget redirections, and priority shifts that made landing impossible on this particular mission. The gap is not a technical failure. It is the accumulated consequence of choices. Dugrenbrand Barnd. Chapter 8. The Kyle of What Lies Beyond. Distabrinland Barn Bond. At this point in our story, I want to step back from the immediate human drama of Artemis II and place 252,000 miles in its larger context. Because one of the things that the coverage of this mission tends to obscure, in its excitement about records broken and records set and the return of humans to lunar vicinity, is how local, how intimate, how almost infinitesimally small this achievement is when measured against the actual scale of the cosmos, 252,000 miles. Let us build up from this number. Earth's diameter is 7,118 miles. The distance the Artemis II crew traveled, the maximum distance of 252,000 miles from Earth, is about 31.5 Earth diameters. If you stacked 31.5 copies of the Earth on top of each other, you would reach the farthest point any human being has ever traveled from the planet's surface. That is the entirety of human exploration measured in Earth diameters, 31.5. Now let us consider the Moon itself, which was the destination. The Moon's diameter is 2,159 miles. Earth to the Moon is about 110 Moon diameters. A human being standing on the Moon's equator and looking at Earth through binoculars could resolve individual cloud formations over the ocean. The Earth would appear as a disk about 4 times larger than the Moon appears from Earth's surface. These are distances that are, in the truest sense, local. They are the spatial scale of our immediate neighborhood, Mars. At its closest approach to Earth, which occurs roughly every 2 years when Earth and Mars are on the same side of the Sun, is approximately 30.9 million miles away. That is 142 times the distance to the Moon. At the speed of the Artemis II mission's translunar injection burn, about 24,500 miles per hour, a spacecraft traveling directly to Mars at closest approach would take approximately 57 days. In practice, a Mars mission would follow a curved trajectory called a Hohmann transfer that takes advantage of the orbital mechanics of both planets, extending the travel time to somewhere between 6 and 9 months for a one-way journey. During those 6 to 9 months, the crew would be exposed to galactic cosmic rays and solar energetic particles at levels that no spacecraft we have ever built provides adequate shielding against. The exposure would represent a significant cancer risk. Estimates vary, but the additional lifetime cancer risk for a 6-month trip to Mars and back could be on the order of several %, which is why radiation shielding is one of the most significant unsolved problems in human deep space exploration. They would also be so far from Earth that radio signals, which travel at the speed of light, would take between 3 and 22 minutes to arrive, depending on where the planets were in their orbits. A conversation in real time would be impossible. An emergency requiring expertise from Earth would receive a response not in seconds, but in hours at minimum. The crew would need to be genuinely autonomous in a way that no crewed space mission in history has required, and Mars is next door. By cosmic standards, Mars and Earth might as well be in the same room. The nearest star system is Alpha Centauri, a triple star system located approximately 4.24 light-years from Earth. 1 light-year is the distance that light travels in 1 year, moving at 282 miles per second. A light-year is approximately 5.88 trillion miles. Alpha Centauri is approximately 24.9 trillion miles from Earth. At the speed of the Artemis II translunar injection burn, 500 miles per hour, a spacecraft traveling toward Alpha Centauri would require approximately 116,000 years to arrive. To put this in human terms, when that spacecraft departed, the most sophisticated human tools were stone hand axes. The first modern humans had not yet left Africa. Agriculture had not yet been invented. Written language did not exist. If such a spacecraft had been launched when the first anatomically modern humans walked the Earth, it would still have 70,000 years of travel remaining. The nearest star is 116, 0 years away at our current best speed. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, depending on how you count them and which estimates of stellar populations you use. It spans approximately 100,000 light-years from edge to edge. To cross the Milky Way at the speed of the Artemis II mission would require approximately 2.7 billion years. The Sun and the Earth themselves are about 4.6 billion years old. This crossing would take more than half the age of our solar system. The local group, the collection of galaxies to which our Milky Way belongs, a gravitationally bound cluster of roughly 50 galaxies of various sizes, spans about 10 million light-years. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. At Artemis II speed, reaching Andromeda would take approximately 70 billion years, 5 times the current age of the universe. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a diameter of approximately 93 billion light-years. It contains an estimated 2 trillion galaxies, each containing hundreds of billions to trillions of stars. Humanity has traveled 252,000 miles from Earth. Against this backdrop, that number does not appear on any scale. It is not just small. It is so small that to call it a rounding error is to vastly overstate its significance. If you represented the observable universe as a map of the continental United States, stretching from New York to Los Angeles, then all of human exploration would fit within a single atom on that map. A small atom, a hydrogen atom perhaps. And within that hydrogen atom, the difference between staying on Earth and traveling to the moon would be smaller than the nucleus. I am not saying this to diminish what Artemis II accomplished. I am saying it because the perspective matters. We exist on a planet orbiting a star in a galaxy among 2 trillion galaxies, and we have collectively managed, in all of recorded history, to extend our physical presence approximately 31 Earth diameters from the surface of our home world. The universe is not hostile to us. It is not actively preventing us from going anywhere. The laws of physics as we understand them permit travel across cosmic distances, given sufficient velocity and sufficient time. But the gap between where we are, 252,000 miles from Earth at our farthest, and where those laws permit us to go is not a gap in knowledge. It is not a gap in desire. It is a gap in capability so vast that it should reframe every conversation about space exploration. We have not escaped the gravity of our home. We have barely tentatively, momentarily moved away from it. The moon is not beyond our reach. It is practically on our doorstep. The stars are beyond our reach in any practical sense. And the universe beyond our galaxy is beyond our reach in any sense at all. This is the context in which Artemis II occurs. This is the scale against which 4,067 miles must be measured. Dotbrunbrun. Chapter 9. The Four. O-flu. In all of the discussion of distances and records and engineering decisions and historical context, it is easy to lose sight of the fact that this story belongs ultimately to 4 specific human beings who chose to do something extraordinarily dangerous and difficult. Commander Reed Wiseman, 48 years old at launch, a naval aviator with over 2,300 flight hours and experience in more than 25 aircraft, a former test pilot who later became a NASA astronaut and flew to the International Space Station in 2014, spending 165 days in orbit. He served as chief of the astronaut office from 2020 to 2023, one of the most demanding and least glamorous jobs in NASA, managing the training, assignments, and careers of the entire astronaut corps while the Artemis program was still taking shape around him. He was selected to command Artemis II-3. Between his selection and the launch, Wiseman spent 3 years in an intense and relentless preparation cycle, simulations in the mission simulator. training on the specific systems of the Orion spacecraft, weeks in isolation facilities designed to recreate the psychological dynamics of long-duration spaceflight, emergency procedure reviews, medical evaluations, public appearances, congressional briefings, and the constant uncertainty of a program that kept missing its own deadlines, kept encountering new technical challenges, kept generating new reasons why the launch was being pushed further into the future. The patience required to sustain readiness across years of uncertainty, to remain focused, to remain motivated, to keep training for a mission that might be delayed again and again and again, is a form of endurance that does not appear in the mission statistics. It is invisible in the press releases, but it is part of what made the mission possible. Pilot Victor Glover, 47 years old, also a naval aviator and test pilot, also a veteran of the International Space Station, where he served as pilot on the first operational Crew Dragon mission, SpaceX's first regularly crewed flight to the station, in November 2020, spending approximately 168 days aboard. Glover is the first Black astronaut to serve as pilot on a crewed lunar mission. He has spoken frequently about what this representation means, not as personal achievement, but as signal, as evidence to young people who look like him that the path to space exploration is open to them. During the mission, Glover described what it felt like to look back at Earth from 252,000 miles and see the planet his family was on, the planet that all of human civilization was on, reduced to a small blue disk in the darkness. He described the feeling not as despair or vertigo, but as clarification, the kind of clarification that comes from seeing something from far enough away that its essential nature becomes undeniable. Earth is small, it is precious, it is the only home any human being has ever had. And from 252,000 miles, that fact is not an abstraction but a physical reality visible through a spacecraft window. Mission specialist Christina Koch, 44 years old, an electrical engineer by training who worked at the National Science Foundation's remote research stations in Greenland and Antarctica before joining NASA, bringing with her the kind of tolerance for isolation and extreme environments that long-duration spaceflight demands. She holds the record for the longest single spaceflight by a woman, 328 consecutive days aboard the International Space Station in 2019 and 2020. She has conducted 6 spacewalks. She is, by any measure, one of the most experienced active astronauts. Koch is the first woman to travel to the moon's vicinity. The history that statement evokes is complicated. Women had qualified as astronauts since 1978. Several had applied to the Mercury program and met the physical and professional eye requirements. But the Mercury astronauts were selected from military test pilots, and women were barred from military aviation at the time. The barriers were not technical, they were institutional, and they took decades to dismantle. Koch's presence on Artemis II does not undo that history, but it extends the map of who gets to go, and that extension matters in ways that are both symbolic and practical. The practical dimension matters because the history of technology is full of examples where the diversity of perspectives among the people building and flying the systems determined what problems got solved and what problems got ignored. Homogeneity in high-stakes technical communities is not just an equity problem, it is a safety problem. Mission specialist Jeremy Hansen, 47 years old, a Canadian Space Agency astronaut and former military fighter pilot who logged over 2,000 hours of flight time in tactical jet aircraft before transitioning to the astronaut corps. Artemis II was Hansen's first spaceflight of any kind, his first time in orbit, his first time experiencing weightlessness for more than the brief periods available in parabolic flight training, his first time seeing Earth from space, his first everything. The decision to include an astronaut on their first spaceflight on a lunar mission, bypassing the conventional career progression that would normally involve at least one ISS stay before a deep space assignment, was deliberate. NASA and the Canadian Space Agency wanted to include an international partner on the first crewed Artemis mission, and Hansen was the Canadian astronaut selected for the assignment. He brought with him not the accumulated experience of previous flights, but the fresh perspective of someone seeing it all for the first time. Hansen later said that the thing he was least prepared for, despite all the training, was the silence of space. Not acoustic silence, the spacecraft, the hum of fans, and the chirp of systems, and the conversation of 4 crew members in a small enclosed space. He meant a deeper silence, the silence of looking out the window at 252,000 miles and realizing that outside the thin metal wall there is nothing. Not air, not temperature, not sound, not the possibility of unprotected human survival. The spacecraft is an island. The universe outside it is, in the most literal physical sense, uninhabitable. He said that the moon, when it finally filled the window during the flyby, broke that silence, not acoustically, but existentially. The moon is something ancient and enormous and real. Seeing it from 4,067 miles was seeing something that exists in the universe beyond the spacecraft. Something that is not just vacuum, something that has weight and history and surface texture and the marks of billions of years of bombardment. He said it made the universe feel less empty, not more. These 4 people live with an experience now that no other human beings alive share. They have been where almost no one has been, seen what almost no one has seen, felt what cannot be adequately described to those who were not there. The 12 Apollo astronauts who landed on the moon are all retired or deceased. The crews of Apollo 8, 10, and 13, who orbited the moon without landing, are all retired or deceased. Of the people currently alive, these 4 are the only ones who have been to the moon's vicinity. That will change. More missions will fly. More crews will go. The experience will eventually become, if not common, at least more widely shared. But for now, for this moment in April 2026, there are exactly 4 people on Earth who know what it is like to see the moon from 4,067 miles away. Dundravon Drand, Chapter 10. What Artemis is actually for Skrundravlin. It is tempting to evaluate Artemis II purely in terms of what it did not accomplish. No landing, no boot prints, no lunar samples, no human presence on the surface. Against the Apollo standard, against what was possible in 1969 with technology vastly less advanced than what exists today, not landing seems like an extraordinary failure of ambition or execution or both. But this framing misunderstands what Artemis II was actually for. And understanding what the mission was for requires understanding something about how human spaceflight programs work that is not intuitive and is rarely explained in public communications. Human spaceflight is not primarily about exploration, it is about verification. Every crewed space mission in history has been at some level a test. The Mercury missions tested whether humans could survive in space at all, whether the physiological responses to weightlessness, vacuum, and radiation were survivable, whether the psychological demands of isolation and confinement were manageable, whether the engineering systems designed to keep a person alive in the most hostile environment imaginable actually worked when a real person was inside them. The Gemini missions tested rendezvous, docking, spacewalking, and the endurance required for the 2-week missions that would precede a moon landing. The early Apollo missions tested the command module in lunar orbit before anyone tried to land. Each of these missions produced knowledge that the missions following it depended on. The knowledge was not theoretical, it was empirical, acquired by flying real vehicles with real people in real space and seeing what happened versus what the models predicted. The history of spaceflight is a history of models being wrong in ways that simulation could not reveal, of discoveries made in flight that changed the designs of subsequent vehicles and the procedures of subsequent missions. Artemis II is the first crewed version of this process for the Orion and SLS system. The life support systems aboard Orion, the oxygen supply, the carbon dioxide removal, the temperature control, the humidity management, the pressure regulation were operated by a real crew for a real 10-day mission duration for the first time. Artemis I tested these systems uncrewed, but an uncrewed test does not tell you everything. Humans breathe, metabolize, sweat, shed skin cells, produce waste, and interact with spacecraft systems in ways that robotic surrogates cannot fully replicate. The real performance of a life support system serving a real crew in real deep space is a different dataset than any ground test or uncrewed flight test can provide. The thermal control system was evaluated under real deep space conditions, the alternating extreme heat of direct solar radiation and the extreme cold of orbital shadow, over a trajectory that took the vehicle through conditions that no Earth-orbiting spacecraft ever encounters. The deep space communications system was tested at actual deep space distances, revealing propagation characteristics and link margin data that ground testing cannot generate. The human factors, how the crew adapted to weightlessness, how they slept, how they performed their duties under the fatigue of the early mission days when the workload is highest, how the interpersonal dynamics of 4 people in a small spacecraft evolved over tens. All of this is data. Irreplaceable, essential data that informs the design of procedures and systems for longer and more demanding missions. The navigation and trajectory systems were exercised over the full arc of a real lunar mission. The propulsion system was fired in real deep space. The heat shield, whose performance under re-entry conditions is the most critical and least predictable aspect of the return, was evaluated with real crew aboard for the first time. All of this produces knowledge that Artemis III, the landing mission, will depend on. If Artemis II had revealed a critical flaw in the life support system, a failure mode in the thermal control, a navigation anomaly that the models had not predicted, those discoveries would have allowed engineers to fix the problem before putting a crew through the far more demanding sequence of operations that a lunar landing requires. The mission was designed not to be the final answer, but to be the penultimate question, revealing everything about the system that only real flight with real crew can reveal. This is not exciting to communicate to a public that grew up with Apollo and has internalized the narrative of first time, never before, historic lunar landings. It is the unglamorous reality of how reliable human spaceflight is built. Incrementally, carefully, expensively, with each mission preparing the next and the gaps between them filled with analysis and refinement and redesign. Here is the sequence that leads from Artemis II to humans actually setting foot on the moon again. Artemis II has verified that Orion and SLS can carry crew safely to lunar vicinity and return them. That verification is now complete. The envelope of the system is known. The models can be refined with real flight data. The procedures can be updated based on crew feedback. The risks of the next mission can be characterized more accurately. Artemis III requires all of that, plus a successful demonstration of the human landing system, SpaceX's Starship variant. The landing system must prove that it can be fueled in orbit, that it can perform autonomous rendezvous and docking with Orion in lunar orbit, that it can carry crew safely through powered descent to the surface, that it can support crew operations on the surface for the planned duration, and that it can ascend from the surface and return the crew to Orion for the journey home. None of these capabilities have been demonstrated with human crew. All of them must be demonstrated, or the risk assessment for Artemis II becomes unacceptable. Between Artemis II and Artemis III, there is an enormous amount of work remaining. The work is real. The timelines are uncertain. The funding required to complete it depends on budget decisions that have not yet been made and cannot be guaranteed. The political will required to see the program through to an actual lunar landing has been tested repeatedly over the history of the Artemis program and will be tested again. The 4,067 miles between Orion and the Moon is not the end of the story. It is the latest chapter of a story that is still being written by engineers and managers and politicians and astronauts and the institutions they work within. Whether the story ends with bootprints in the lunar soil at the South Pole, or with another canceled program and another generation of frustrated intentions, depends on choices that extend far beyond the technical capabilities of the systems involved. Dudbroom, Chapter 11. The Fragile Planet, Sudbroom, Dudbroom. Victor Glover looked out the window of Orion at 252 miles from Earth and described the experience as seeing living proof. Living proof of what? Of fragility, of the extraordinary specificity of the conditions that make life on Earth possible, of the gap between what Earth is and what the rest of the universe is. There is a photograph that changed how humanity thought about itself. It was taken on December 7, 1972, by the crew of Apollo 17 during the outbound journey from Earth to the Moon. The photograph shows Earth as a fully illuminated sphere, Africa and Antarctica visible, swirls of cloud over the Southern Ocean, suspended against the absolute black of space. It became known as the Blue Marble. It is estimated to be one of the most widely reproduced photographs in human history. What the Blue Marble did, what no previous image of Earth had done with the same impact, was make the planet's boundaries visible. For all of human history up to that point, the sky appeared to merge seamlessly with space at the horizon, and Earth felt continuous with everything. The photograph showed otherwise. Earth was a ball. It had edges. It floated in nothing. Its surface was covered with water and cloud, and the thin brownish-green smear of land that supports all terrestrial life. 54 years later, the crew of Artemis II saw the same sight. From farther away than the Apollo 17 crew when they took their photograph, farther away than any humans have been in the interval, they saw the same blue ball, smaller now, reduced by the additional distance to something closer to a marble than a ball, smaller than a thumbnail held at arm's length, surrounded by the same absolute blackness. From that distance, every border that divides humanity against itself is invisible. Every political dispute, every territorial conflict, every ideological division that seems fundamental and irreconcilable from inside it, from 252 zeros miles, none of it has any scale. You cannot see countries, you cannot see cities except at night, and from that distance even the city lights are too faint to distinguish. What you can see is the planet. One thing, indivisible, with an atmosphere so thin that its presence is revealed only by the slight blue tint around the limb. That atmosphere, the layer of gas that makes the planet habitable, extends to a technical boundary of roughly 62 miles above the surface. If you scaled Earth down to the size of an apple, the entire atmosphere, including the layers too thin to breathe, would be thinner than the apple's skin. This near-nothing is everything. It is the pressure vessel that keeps the oceans from boiling away into space. It is the radiation shield that attenuates the solar wind enough that DNA is not constantly being disrupted at the surface. It is the medium that carries weather, that distributes heat from the equator to the poles, that makes the temperature range on Earth compatible with liquid water over most of the surface most of the time. Remove the atmosphere, not catastrophically, but gradually, as happened on Mars billions of years ago, and the surface temperature swings between extremes that no complex biology can survive. Remove the liquid water, as has happened on Mars and Venus for different reasons, and the chemistry of life becomes impossible. Remove the magnetic field, which protects the upper atmosphere from solar wind erosion, and the atmosphere itself gradually leaks away into space as it did on Mars. Earth has all of these things in the right proportions, not by design, or at least not by any design we understand, but by the coincidence of planetary formation, by the presence of a large moon that stabilizes the planet's axial tilt, by the position of Earth in the solar system's habitable zone, by the timing of a giant impact 5 billion years ago that may have been essential to giving Earth its magnetic field and its moon simultaneously. From the surface, the scale of what makes Earth livable is impossible to feel. The sky appears infinite, the ocean appears inexhaustible, the land extends to every horizon. From 252,000 miles, none of that scale holds. The planet is a small sphere with a thin shell of complexity that makes it different from every other object in the observable universe that we know anything about. Glover saw this and called it living proof of fragility. Koch saw it and thought about responsibility. Hansen saw it for the first time and had no adequate words. Weismann, who had seen it before from orbit but never from this distance, said it changed the number but not the feeling of Earth as something specific, particular, irreplaceable. The paradox of human space exploration is that the farther we go, the more clearly we see what we are leaving behind. The exploration that is supposed to be about expanding outward keeps turning our attention inward, back to the planet we came from. Every astronaut who has traveled far enough to see Earth as a world, rather than as a landscape, comes home with a different relationship to it. Whether that different relationship is translatable, whether the experience of the few who go can meaningfully change the perspective of the many who stay, is one of the unanswered questions of the space age. The blue marble photograph changed something in collective human consciousness, if only briefly. Whether Artemis II will produce images with that kind of power, whether the sight of 4 people circling the moon in 2026 will feel as profound as the sight of 2 people stepping onto it felt in 1969, is something we will learn as the weeks and months ahead reveal how the mission is remembered. Dugrin, Jerned. Chapter 12. Proximit is not Adaran, Jerned. There is a philosophical thread running through the entire history of human lunar ambition, a thread that the Artemis II mission makes visible with unusual clarity. We are very good at getting close. In 1968, Apollo 8 flew to the moon and orbited it, bringing humans within 69 miles of the surface, close enough to see individual boulders in the walls of craters, close enough to watch the Earth rise over the moon's horizon in the photograph taken by astronaut Bill Anders that became known simply as Earthrise. They did not land. They orbited 10 times and came home. In 1969, Apollo 10 flew a full dress rehearsal for the landing, separating the lunar module from the command module in lunar orbit and descending to within 47,400 feet of the surface. They photographed potential landing sites. They tested the guidance and navigation systems. They did everything that the landing mission would do except the actual landing. Then they ascended, redocked, and came home. Then Apollo 11 landed. Then 5 more missions landed, the last being Apollo 17 in December 1972. Then for 54 years, the closest any human came to the moon was low Earth orbit. Then Artemis II came to 4,067 miles. Each time we have approached the moon in the Apollo era, and now we have arrived at the threshold and discovered that the threshold is not the hard part. Getting to the moon's vicinity, as Apollo 8 and 10 demonstrated, and as Artemis II now confirms, is technically achievable with sufficient investment. The hard part is everything that comes after the threshold is crossed. Proximity is not arrival. Being close is not being there. 250,000 miles is not 250,000 miles plus 4,000 more. This matters because the history of human exploration is full of moments where proximity was mistaken for arrival, where closing most of the distance was treated as equivalent to closing all of it, where the celebration of getting close substituted for the sustained effort required to actually get there. Columbus reached the Caribbean in 1492. He made 4 voyages and established settlements that failed. He died without fully understanding what he had found or how to sustain a permanent human presence in the Western Hemisphere. The permanent European presence in the Americas came from those who came after him, who had the benefit of his charts and his failures and the knowledge accumulated through his repeated attempts. The first expeditions to reach the vicinity of the South Pole in the early 20th century were preparation for the expeditions that actually arrived. Amundsen and Scott reached the pole itself in 1911 and 1912 respectively, Scott's party dying on the return journey, but even their arrival did not constitute a sustained human presence. The first permanent Antarctic stations were not established until the International Geophysical Year of 1957-1958, nearly half a century after the first human footprints in the polar snow. The pattern is consistent. Getting close is the first act. Actually arriving and then sustaining a presence is a different and harder act that requires different capabilities and different kinds of will. Artemis II is the first act. The question is whether the second act follows, or whether the gap of 467 miles becomes another 50-year pause in human lunar ambition. The danger, the historically grounded, evidence-supported danger, is that we celebrate the genuine achievement of Artemis II in ways that substitute for the harder work of actually landing. That the records broken and the distance covered become the story, and the 4,067 miles that were not covered fades into the background of a narrative about progress and achievement that does not actually include getting to the surface. The moon does not care. It has been orbited and approached and photographed and admired and used as a target for ambition for decades. It has been reached and left and nearly reached again. It does not register our proximity or our departure. It continues in its orbit regardless of our intentions toward it. We are the ones for whom the gap matters. We are the ones who feel the distance as a measure of failure or progress, who experience the 4,067 miles as significant, who understand that touching the surface is different from circling above it. And we are the ones who will decide whether those 4,067 miles are a temporary gap in an ongoing program of lunar exploration, or the latest in a series of approaches that ultimately lead to retreat. Ungrun, Undreen. Chapter 13. The Last 4,000 Miles Dream. The Orion spacecraft named Integrity entered Earth's atmosphere above the Pacific Ocean on April 10, 26. The re-entry sequence lasted approximately 13 minutes from the moment the heat shield made significant contact with the upper atmosphere to the moment the main parachutes deployed at lower altitude. 13 minutes during which the heat shield performed the function it was designed for, ablating and charring and carrying heat away from the capsule, while the plasma of ionized air surrounding the vehicle created a blackout period during which no radio communication was possible between the crew and mission control. 13 minutes during which the flight directors, who had been awake for most of the mission, sat in front of their consoles and watched data stream in from the capsule's sensors, and waited for the communication blackout to end and for the crew's voices to return. The voices returned, the parachutes deployed, The recovery ship USS John P. Murtha moved into position. Divers entered the Pacific Ocean around the floating capsule. The hatch was opened, one by one. 4 astronauts who had traveled farther from Earth than almost any human being in history were helped out of their spacecraft and into the Pacific air of a Southern California afternoon. Raid Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. Home. It covered a total distance from launch to splashdown of approximately 695,081 miles. The crew broke the distance record set 56 years ago by the crew of a damaged spacecraft trying to survive. They tested the most capable crewed spacecraft ever built by the United States in the environment it was designed for. They photographed the moon from closer than any human in half a century. They looked at Earth from farther than any living person had previously seen it. They did not land on the moon. Both of these things are true simultaneously, and both of them matter. The moon is still there. As the recovery ship moved through the Pacific swells and the crew underwent their post-mission medical evaluations, checking for orthostatic intolerance, for bone density changes, for the cardiac adaptations that extended weightlessness produces, the moon was rising in the east somewhere, or setting in the west, or invisible below the horizon, continuing its orbit without awareness of what had just happened in its vicinity. The surface is unchanged. The craters are where they have always been. The boot prints left by the Apollo crews are still there, exactly as they were the moment each crew lifted off and left them behind. The equipment abandoned on the surface, seismometers, laser retroreflectors, flags bleached white by decades of ultraviolet radiation, the descent stages of 6 lunar modules, the rover left on the surface by Apollo 17. All of it remains motionless in the airless permanence of the lunar environment, unchanged by the passage of time in the way that only places without weather or biology can be unchanged. The boot prints will outlast every building and monument on Earth. They will outlast the civilization that made them. In 1 billion years, the solar system will have changed in ways we cannot predict. But those boot prints in the lunar regolith will still be there, slightly eroded by micrometeorite impact and cosmic radiation, but recognizable, their ridged pattern still visible to anyone with sufficient resolution to see it. They are waiting, not because the moon waits, but because we project waiting onto things that are simply continuing to exist. The moon does not wait for us. The moon does not have a relationship with us. Only we have a relationship with the moon, and only we experience the gap between what we have done and what we intended to do as significant. Chapter 14, What Comes Next? After Artemis II, the question is Artemis III. The third Artemis mission is designed to actually land on the moon, the first human landing since December 1972, the first human contact with the lunar surface in over half a century. The target is the lunar South Pole, a region that has never been visited and that scientific analysis suggests contains resources of enormous practical importance to the long-term human presence on the moon. The lunar South Pole is one of the most extreme environments in the inner solar system. Some crater floors near the pole have not received direct sunlight in billions of years. The geometry of the moon's small axial tilt, only about 1.5 degrees, means that the sun always stays close to the horizon as seen from the poles, and certain crater floors are in permanent shadow. These regions have temperatures that can fall below -400 degrees Fahrenheit. They are, in some cases, colder than the surface of Pluto. In these permanently shadowed regions, scientists believe water ice has accumulated over billions of years. Comets and asteroids have delivered water to the moon throughout its history. On the sunlit portions of the surface, that water would be quickly split by solar radiation and lost to space. In the permanently shadowed craters, it can accumulate and persist. Measurements by orbital spacecraft, including India's Chandrayaan-1 mission and NASA's Lunar Reconnaissance Orbiter, have detected signatures consistent with water ice in these regions. Water ice is a resource of extraordinary strategic importance for sustained lunar operations. Water can be used directly for drinking and for the hydration of food. It can be split into hydrogen and oxygen by electrolysis, a process that requires electricity, which solar panels near the poles can provide during the near-continuous sunlight available on crater rims. Liquid hydrogen and liquid oxygen are the most energetically efficient chemical rocket propellants available, the same propellants used in the upper stages of the Saturn V and SLS rockets. If water ice at the lunar poles can be extracted and processed in sufficient quantities, it becomes possible to manufacture rocket propellant on the moon from local resources. This changes the economics of sustained lunar operations profoundly. Instead of launching every gram of propellant from Earth's surface at a cost measured in tens of thousands of dollars per kilogram, missions could refuel on the moon from ice that has been sitting there since the solar system's early history. This is why the South Pole is the target. This is why Artemis III is not simply going back to Apollo's equatorial landing zones, which are well understood and comparatively accessible. The equatorial zones have been there. The science has been done. The South Pole is new territory with resources that could define the future of human activity in the Earth-Moon system. Getting there requires the human landing system, specifically the SpaceX Starship variant optimized for lunar operations, a vehicle that has never carried crew to any surface, let alone the moons. The qualification process for Starship as a human landing system is extensive and has progressed more slowly than the original Artemis III schedule anticipated. Uncrewed landing demonstrations must precede crewed operations. The docking interface between Starship and Orion must be tested in orbit. The life support systems, the crew equipment, the operational procedures for the surface activities, all of it must be developed, verified, and practiced before the first crew steps aboard a Starship for the descent to the moon. Beyond the technical requirements, the schedule for Artemis III depends on sustained funding that crosses political administrations. The Artemis program has already survived 2 presidential transitions. Each transition brought new leadership to NASA, new scrutiny of the program's costs and timelines, new pressure from competing priorities. The program survived those pressures. Whether it survives future ones, whether the will to actually land, to close the remaining gap, persists through whatever political changes occur between now and the mission's eventual launch, is a question that no one can answer in advance. History suggests caution. Constellation was canceled. Shuttle was canceled. Apollo itself was canceled before it completed its planned missions. The pattern of ambitious human spaceflight programs launched and then abandoned is consistent enough that optimism about any specific program's survival requires active justification, not mere assumption. But history also shows that programs do succeed. Mercury, Gemini, and Apollo succeeded. The International Space Station was built despite years of cost overruns and delays and threats of cancellation. The Hubble Space Telescope was launched with a flawed mirror and then repaired by spacewalking astronauts to become the most productive scientific instrument in history. Artemis could join this list of programs that survived their difficulties and achieved their goals, or it could join the longer list of programs that did not. We are in the middle of the story and cannot see its end. What we know is that as of April 10, 2026, the gap between any human being and the lunar surface stands at a specific number of miles, a number that has fluctuated over the past decade as the program has advanced and stalled and advanced again. 4,067 miles at closest approach. 0 miles briefly 12 times between 1969 and 1972, and then the gap again. The next mission will try to close it. Whether it succeeds, whether the attempt is made, whether the program survives to make the attempt, all of this is still to be determined. Dergrenbrun Brain, Chapter 15, Closing, 6 known Dern Brain Bowl. Tonight, somewhere in the Pacific Ocean off the coast of San Diego, a splashdown recovery operation has concluded. 4 astronauts are aboard a Navy ship, being evaluated by doctors, eating their first fresh food in 10 days, sleeping in beds that do not drift in 0 gravity. The moon is where it has always been. There is something that happens in the mind when you truly try to hold 2 things simultaneously: the magnitude of what Artemis II accomplished and the magnitude of what it did not. Both are real. Both matter. The refusal to pretend that one cancels the other out is, I think, the most honest way to understand the mission and what it tells us about where we are. We accomplished something real. 4 human beings traveled 250,000 miles and returned safely. The records were broken, the systems were tested, the data was collected, the knowledge was acquired. This is not nothing. In the long, expensive, incremental business of building the capability to sustain a human presence beyond Earth, this mission was a real step forward. We also did not land. The gap remains. The surface of the moon was seen from 4,067 miles by 4 pairs of human eyes, and then the spacecraft turned its back and came home. The boot prints from 1972 are still the most recent human marks on any surface beyond Earth. These 2 things coexist: the achievement and the gap, the progress and the distance remaining, the mission that succeeded and the mission that has not yet happened. Here is what I keep returning to in thinking about Artemis II and what it means. The distance between proximity and arrival, that 467 miles, is not a physical problem. We know how to close it. The engineering is understood. The physics is known. The capability gap is real but not fundamental. Given sufficient time and investment, given the political will to sustain the program through its remaining challenges, the gap will close. Humans will stand on the moon's south pole. Bootprints will mark new ground that has never been touched. What is uncertain is whether the will exists to sustain the program through what remains. Whether the celebration of Artemis II's genuine achievements will generate the continued public and political support that Artemis III will require. Whether the lessons learned from 54 years of interrupted lunar ambition have actually been internalized by the institutions that control the program's fate. Victor Glover looked at Earth from 252 0 miles and saw something small, something that needs to be protected and cherished and not taken for granted. He saw what the astronauts of Apollo saw, that Earth is not infinite, not inexhaustible, not guaranteed to remain as it is forever. He saw that the project of extending human presence beyond this single world is not a luxury, not a vanity project, not a distraction from the serious work of managing the civilization we already have. It is perhaps the most serious long-term project civilization can undertake, the one that could eventually mean the difference between a species confined to a single planet, all of its eggs in one fragile basket, and a species that has learned to live in more than one place in the universe. That project is not complete. It is barely begun. Artemis II is a chapter in the opening pages of a story that may take centuries to unfold, if it unfolds at all. The moon is the first page. Mars is pages further on. The rest is unwritten, but the story continues. And it continues because 4 human beings named Reed Wiseman and Victor Glover and Christina Koch and Jeremy Hansen agreed to sit atop 8 million pounds of thrust and fly into the void toward a world they could see but not touch. And to do this knowing that the gap they could not close was not a failure but a beginning. Knowing that the 4 067 miles between them and the surface was not the end of the journey, but the evidence of how far the journey still had to go. They went, they came back. They carried with them data and photographs and the physical memory of seeing Earth from far away and seeing the moon from close enough to count the craters. They carry it still, in the particular way that experiences that most people will never have are carried by those who have had them, with a weight that is not burden but gravity, the gravity of having been somewhere that changes the coordinates of everything else. The moon has been there for 4.5 billion years. It will be there when the next crew approaches. It will be there when the first crew lands. It will be there for the 100 crews after that, and for whatever comes after humans, long after the boot prints from 1972 and the boot prints from future missions have been joined by more boot prints than anyone alive today can imagine. The moon does not wait. It simply is. We are the ones who wait. We are the ones who feel the gap. We are the ones for whom those last 067 miles, those last miles between being close and being there, carry the weight of everything we have not yet done and everything we intend to do. That weight is not a burden. It is a direction. Good night. And keep looking up.